Uh, Today we have Carson Knoll and Chris Harnowski reviving smart card analysis. Let's give them all a hand.
Good. Very good morning. We're more than delighted to be back on a topic that has been a regular occurrence at BlackHat, mostly pushed through Chris over here. That is analyzing smart cards. Those miracle little chips now taking over every application that doesn't seem to know how to help security in any other way. So it seems the last fortress left where people are flocking to that really want to protect secret information. I'm glad to be being here with Chris Harnowski from FlyLogic, a lab down in San Diego that primarily focuses on smart card analysis, equipped with really cutting edge equipment. I'm Carson Knoll from a research lab in Berlin, with a somewhat wider focus on various security topics, and typically try to find attack vectors that don't require very specialized equipment. So the synergy of both will be today an attack that really limits the resource need to take out code of some of the most widely used smart cards. We want to get across mostly one point. If you are a software person, now is the time to start looking into smart cards, because smart cards have, on the hardware side, become so good that the weakest link are the software pieces that not the designers of the chip, but the users of the chip put on there. However, since smart cards were created for one purpose, but today they're abused for another purpose, the one purpose being the protection of secret keys, the other purpose being protecting proprietary code and covering up from analysis. Since this barrier of very strong hardware holds, we want to take that barrier down and give people access to the code running on smart card chips as they're deployed in the field today. So that I imagine most of you are software people, so that you guys can start analyzing smart cards without much hardware expertise. All right, we'll start off with some background on smart card architectures. Some of you may never have seen or gotten explained a smart card chip. We'll then show how we, from one of these chips, reverse engineer the crucial function that now allows this extraction of code pretty easily. This one just stands as an example for a problem that will be found in every smart card chip out there pretty much, though. And we'll eventually cover some mitigation measures smart card manufacturers could do to prevent this. However, before they do this, I hope you will spend years of extracting lots of code for analysis. Prominent example where, one prominent example at least, where code is hidden in smart cards so well that the code can pretty much be as weak as it wants, our credit cards, the EMV credit cards. So still, nobody knows what's really going on inside these cards, even though hundreds of millions have been deployed. And every time people look at it as a black box analysis subject, they do find serious flaws, that they don't distinguish between the signing mode and the pin code mode, that they're heavily reliable to relay attacks even over large distances. All of this would have been spotted in an independent review, I imagine, but there hasn't been any independent review. So once again, we want to encourage you mostly to look at smart card code, and we'll provide you a way of extracting smart card code easily. If you are at the verge of software hardware, we want to additionally encourage you to repeat what we'll explain throughout this talk on other smart card chips, since we have exemplified on one, but there's plenty more out there to be broken.
This kind of comes back to like pen testing. 10 years ago, nobody did any pen testing on their software. The engineers reviewed their own software. Today, companies are making millions a year pen testing for Microsoft, for anybody that's producing products. So this is the pen testing of tomorrow, in a sense.
Right, and of probably much lower hanging fruit. So you'd be looking at most 64K of 8051 assembler code not obfuscated, right? But this may be relevant for hundreds of millions of instantiations. So try to find a software that's as easily analyzable with such big impact of, say, your fuzz testing tool or whatever you use to analyze software today. Right? So a few basics on these chips. They're being found in numerous applications today. In fact, every embedded device pretty much includes a smart card today. They started off in pay TV mostly. This is where this war between people trying to hide information and the people who you give that information to trying to extract it, the pay TV customers, started off first. So this has been an ongoing war for at least a decade and a half, maybe 2 decades. And pay TV is still one of the most competed for industry. However, the same chips, the same protection promise, you can give to your customers a secret that they themselves can't even get to. Of course, carried over to bank cards. Every ATM card that comes with a chip will try to hide some information from you. It now carries into all the mobility domains where every smart meter needs to protect something from its customer. Every smartphone will have to hold up some DRM level, some link to the App Store or whatever. So these same chips are now found everywhere. And there's really only 5 relevant manufacturers that may have one current and one ramping down product. So if you could spend time on breaking 10 smart card chips, you break every instantiation of smart cards out there, really. And so the impact, as I keep on repeating, of doing these analyses is much higher than analyzing single pieces of software we traditionally find in a PC environment, where you find a bug in that one version of that DLL in that instantiation of an operating system, say.
We see a lot of reusable code, too, in the architectures that we bust, because a lot of these people take the libraries, software libraries from their manufacturer. So once you've done one manufacturer, you'll see the instantiations on PowerUp and such, and things like this, and this 2 different ROMs with a lot of similar code in some spots, library functions.
Exactly. So of these 5 smart card manufacturers, they would sell, say, a phone SIM card chip to only 3 relevant companies. They would put an operating system on them, and really every SIM card in each of the, what does the GSMA claim, 6 billion SIM cards shipped. So each of these 6 billion will come with one of 3 operating systems, pretty much, right? And some problems in say the Java interpretation code on these SIM cards has been uncovered for many years. So big analysis lever. But let's look at a smart card chips as an example for many other smart card chips, since they're all pretty much built the same way. What a smart card is a full computing system scaled down to a single chip. It will include a CPU core. It's hidden under this plate of metal. So this is the CPU core on this chip. It includes memories. So there's a read-write memory over here. There's some read-only memory here. And then there's 2 portions of RAM. So really everything you would expect in a normal computer. And since this processor core is really, really slow, it's maybe 20 megahertz, 15 megahertz at 8 bits, it has some supplementary coprocessors. So in here, you'll find an AES engine, I believe. Some others come with ECC accelerators, RSA, and so forth. So the crucial operation that they do very fast, and everything else around it kind of slow. So that's the smart card in a nutshell. And maybe while on this picture, let me point out the 2 dominant kind of streams of attack people have been doing, initially against pay TV cards, today against all kinds of devices. People either read out memories, just look at them optically and infer what code is stored inside. And then, without even doing anything with the card itself, we've tried to find protocol level exploitable bugs in these cards. So that was the very first attacks, and they kind of died down because these cards started defending themselves against optical readout by encrypting everything in the memories. We'll get to that in a minute. The second line of attack was to analyze the living chip, the running chip, and put tiny needles onto some of the data lines of this huge maze of data lines. There will be some that carry the relevant code, the secret keys or the instructions executed. And that's what Chris specializes in. And some of you may have seen his BlackHat DC talk from a year and a half ago, where he actually demonstrated how he found the 8, in this case, since 8-bit architecture, lines on this chip, and he cuts through some structures on top with fibs and with lasers, and then put little needles on each of these tracks. So that's the second line of attack, and the one that really for the last 10 years was the relevant one in a sense that all the chips out there were hacked using this technique.
But like you said, they're getting smaller, they're getting harder to probe, but they're still visibly visible by either electron microscope, focused ion beam, optically. There's all sorts of ways to visually see what you're up against, not just via physically invading it with needles.
Exactly, to illustrate it on this chip. So all of these memories will talk on some common data bus that's probably routed throughout this big MMU maze in the middle, and then put into the CPU core from here. However, before hitting the actual CPU core, that's just this part up here, there's this block of logic, and this is a decryption function. So really everything that's coming from the memories is encrypted until flowing through here, and only when it's jumping out of the decryption function, just before it's hitting the CPU core, that's the relevant data. That's the data you want, right? So
it's also important to note that those tracks are so protected. They've routed them on metal 1.
Okay.
Even below, even deeper, knowing that that's the only clear point.
So this is of course a 3D structure. Chip isn't just a 2D structure. There are gates on the lowest level. That's kind of a functional unit, and then there are several layers of routing on top where little metal wires connect these functional units. And as Chris just pointed out, the crucial wires you put on the lowest possible routing layer, and then you put other stuff on top. So with your little needles, you can't get there anymore. And in fact, they not just take the stuff that they already route to put it on top, but they put meshes. We'll get to that in a minute too, to make it additionally harder. So all of this is saying that this is the attack vector smart card manufacturers have been considering in building new chips for the past couple of years. It's a real arms race. The machines probably needed for this double or quadruple in price every time they come up with a new chip generation. This first attack vector, though, the one where people optically read out the memories, that has, they think, been solved by encrypting the memories and hasn't really been considered ever since. So the first such memory encryption was in a chip from 1999, yeah. I think, and ever since the industry thinks they solved that problem. But of course, every problem is coming back, and now it's 2011, and the problem is back with this talk. To illustrate what people did back in the day, here's two pictures of different types of memories and how you can optically read them out. So there was no expensive equipment needed. Well, in these cases, maybe, because the imaging equipment is pretty good. But with a lot of chips, you can just use a simple microscope to snatch pictures like these from chips. And you can clearly distinguish the ones and the zeros. Right? They're different per memory, how they exactly created 1 and a 0, but you definitely see patterns through here. And in the right chip, you even see a pattern that ends in just 1, so FF. So this is the end of this ROM. telling us that since we can read it optically, this is not encrypted, of course. If this was encrypted, every F would translate to something different, right? So this is how people back in the day broke those cards, and we want to bring that cheap type of analysis back. What's hindering us, of course, is this encryption function between the memories and the CPU, where the data has to be decoded, right? So we'll show you how we reverse engineered one of these. And some of you may be familiar with our work on the MIFARE chip. So this is a direct follow-up on what we did back then, just targeting a completely different part of the chip. So in the MIFARE work, it was basically the protocol the chip would use to speak to the outside world, whereas this function here that we reverse engineer is completely secret and hidden from the outside world. There's no specification that even says it exists. Right. So it's a self-protect feature of the chip, and one that as I keep saying, is being abused to hide bad protocols from analysis. To give you a somewhat larger outlook of the relevance of this result, we didn't just reverse engineer one chip, but instead created a tool chain to do it to any chip, really. Since this chip we keep looking at isn't the only one. It was the first one to have this idea. Today, every chip, not just smart card chips, every chip, the hardened chip, will have some type of memory scrambling or some type of memory encryption. So this really applies to every chip. Most of the newer chips don't nicely separate the encryption function from the CPU code, though, and we'll put everything in one big bunch to supposedly make it harder to find the relevant pieces to reverse engineer. So a more recent chip would look like this, where you can still clearly tell where the memory areas are, but all the other things, the MMU and the CPU core, the memory encryption, and the crypto accelerators, they are all merged into this big blob in the middle. Right? This chip is a lot bigger than the other one, too. So there's more functionality, but less structure to it. An idea that supposedly is even patented, but everybody is doing it today. Right? Yeah. It even comes more natural as you more automate your tool chain, your chip creation tool chain.
Does anybody have any questions? Are we? Nothing? Go ahead.
Why did you decide to go this way? Why did you intuitively decide that you wanted to take this? I mean, these attacks, I know you guys have been doing this for a long time. Why did you decide that this is the direction that you wanted to go to investigate it? What motivated you from your prior work to get to this place?
So the question was, why did we follow this type of attack? I guess rather than extending on what Chris keeps doing, finding the relevant points and then putting needles on them. What we wanted to show with this is that smart cards are exposed to much larger risks than typically thought. So it's not an equilibrium of powers where you'd have to buy a multi-million-dollar machine to break a chip out of which you can maybe extract a couple $1 million. But rather, the analysis can start at much cheaper equipment, not necessarily uncovering all the data you need to, say, copy a pay TV card, but all the data you need to do the security analysis on the pay TV card, and then perhaps find vulnerabilities somewhere else, not in the hardware, but in the software running on the chip. So this is meant as a cheap enabler for deeper analysis rather than an attack vector to established systems.
And where we're about to go is going to show you these tools that he's talking about right now. We need those tools because things are no longer so modular, like he's showing you this nested glue logic. Today now you've got to actually trace out and actually study some of the gates if you need to figure out the function. But even a lot of times the function isn't even necessary because it's usually an LFSR with an XOR, things like this. They can't do much, they don't have a lot of time.
Right. So if everybody's clear on now how smart cards work conceptually, there's a question in the back.
Chris, would you mind talking a little bit about the filtering process that you use to determine the data channels after the MED encrypted data and how
I can't hear your question.
I think the question was how did you find the data wise after the MED? What's the process involved?
It depends on the CPU. I can talk to you about it afterwards, though. It just depends on architecture.
But generally, I guess a good generic strategy would be find the elements on the chip that take in the data. That would be the instruction latches. Find 8 or 16, maybe 32 of them, depending on the architecture. And if you found on this chip 8 same flip-flops, then you have a good chance that the inputs to those are the relevant
But it all begins tracing from like the ROM output, let's say, because you know the chip runs from ROM on power up. They always will. They have to. It's the only static block of code there. So I mean, follow your ROM outputs. You sit on them with needles. I mix techniques. So I'm mixing what Carson's talking about today with my other known techniques. So it all depends, but we can discuss it after. So.
Mm-hmm. There's one more question over there. So the question is, are there like second level caches that would complicate this? I don't think there are caches
really
on smart cards. No, every
on,
memory access is in one clock cycle anyway.
Right, but there are some CPUs like the 88 from Infineon has a data cache, instruction cache. It can help you, but it doesn't really hurt us or help us in any way. I can't hear him. I can't hear you.
I think that's getting too specific. Find us later. We'll discuss caches with you then.
Yeah.
One last thing on one last kind of example of how the smart card industry is fighting the one threat but not the other. So the number one security features on all the chips over the last 10 years was a mesh. So a little snake of metal put on top of the entire chip. So no matter how tiny your needle is, there's no way of getting to the relevant points in the CPU core without breaking this mesh. And the chip notices, because this is a long snake, of course, so it can test whether it's still connected. So breaking and making better and breaking these meshes has been part of the arms race. However, of course, for what we now want to do, just look at the ROM bits, maybe reverse engineer some static function. We take away the mesh, we don't care. It's just one more minute polishing the chip down to get rid of this mesh. Just to illustrate how the evolution has ignored the reverse engineering threat. So we want to reverse engineer this one memory encryption function to illustrate that it could be done to any chip, really. And we're working on a couple more. One we're done with, though. And so the challenge we're facing is one that in the software world was solved a long time ago. The one that you want to recover a human-readable instantiation of an algorithm from a machine-parsable instantiation, or from a non-human-readable instantiation. And it's kind of the reverse process to compiling. So you start with a human-readable instantiation, of course. You compile it, and then somebody disassembles it and reconstructs what this algorithm has been in the first place. So in the hardware world, the one direction, of course, exists. That's how chips are being built. The other direction, though, hasn't so far. And we spent, ever since the MIFA work, the last 4 years, building a tool that can act as a silicon disassembler. So that takes whatever exists in this case, the physical world, and brings it back to a human-readable algorithm. And there have been a couple of bachelor and one master thesis going into improving this tool and scaling it up so that today we feel confident that this really applies to entire smart card chips, where before we were really limited to tiny algorithms. But there's nobody saying this couldn't be scaled up to, say, an Intel processor. Probably a couple more master theses would be needed to work on some of the scalability questions.
It reminds me of IDA back in the old days compared to IDA today. So
oh yeah, exactly.
The old IDA today, but it's
so we have like an alpha version of the first IDA Pro now in hardware. Yeah. And the process surrounding this a little more involved than just software reverse engineering, since it has to start at a couple of steps, bringing data into the computer, on which then this disassembly program can act. I'm not going to go into much detail here, but it still involves the same processes we did on the MIFA, polishing down the chip to different layers and taking pictures under a decent microscope. That's pretty much it. And you can, of course, outsource this to, say, labs in China. They'll do this through a full smart card chip for a couple of thousand, but if you already know what you're looking for, maybe it was a couple of hundred.
Even in the States, there's $400 a layer.
Okay, $400 a layer, so here we go. And at that point, it's really just data processing in a computer, and in this case, image analysis problems mostly. So as I said, we spent the last 4 years scaling this up in mostly. Well, it became more scalable in two respects. First of all, the skill required to use it was much decreased. So initially, we built this for a tool for ourselves to use. Now we really imagine people very low skilled, hopefully cheap too, in a distributed network working on chips together. The tool is already collaboratively, so many people can work on one set of pictures at the same time. So that's the one dimension it scaled in. The other one is the expressibility of the results. So initially, it gave us some guidance how this circuitry could work together. Today, it's exporting synthesizable Verilog or VHDL code. So you could take what comes out of the disassembler and again throw it into the compiler and build a new chip. Probably this will be much, much slower and not quite as elegant as the original chip, but functionally it would be the same. Right? So the results are really what comes out of a disassembler, some form of understandable code that then still somebody needs to work on and name things and reorder. You know what you do in IDA Pro. Right? So that human step at the end is still not too scalable, but also it's the most fun step. So probably wouldn't want to scale that away. So long story short, here's the tool. It's called D-Gate by Martin Schobert out of Berlin. And so looking at static pictures here, let me just fire this up. It's open source, always has been. dgate.org runs on or compiles on Mac and Linux, probably on Windows too. I don't think anybody has tried. So, for instance, this is a small part of this memory decryption function we reversed, and this is already showing the gate instantiation. So a gate will be a functional unit, for instance, an XOR, right? So here's an XOR, here's another XOR that is placed on a 2D map of functions, and then, as we were saying before, there are metal wires connecting these, and there's several layers of these. In this case, only two for the MET, and there's others on top for bigger routing, I think. So the tool helps you in recognizing these structures. We already went through this step, where you tell it, hey, there's some function over here. And maybe if I take away the so there's some function over here. It's kind of a closed unit, so you can tell that this is one functional part. It's probably hardest to tell on these pictures of all pictures we ever looked at, since the designers of this chip specifically did obfuscation. So they tried to blur the borders. But if you look at it from with some patients, you see that this structure is reappearing over here, for instance, is appearing over here. So this seems to be one basic building block. And in fact, the ones in between are the exact same thing, just mirrored. Maybe you see this arc, this arc, right? So there's the same basic Lego block used a couple of times here. And if you tell the software, hey, here's one gate, it will find all the other gate instantiations on the entire chip. For this memory encryption, there's just maybe 25. Sometimes in other libraries up to 40, but never really more than 50. I don't think we've seen a library with more than 50. So you do this 50 times. Finding places on the chip where no gate is marked yet, and you mark it, and it finds all the other places, and you get quick coverage. You then have to name them, of course. You have to say that this is an exon. As I said, this is an obfuscated chip. So you actually have to draw out the transistors and how they're connected to each other. Or you send the pictures to us. We'll do it for you. There's
or to Jerry Ellsworth.
Yeah, exactly. She cracked that challenge in like
fast.
a minute. Yeah. So there's a webpage that illustrates a lot of this. It's called siliconzoo.org, where there's a lot of different libraries with names attached to them. So you can look at how typically they look very similar to each other. This one being a very exception since it's obfuscated. So you find all these gates in that process I just described, and now it's really
making more sense.
Yeah, and now it's really just dumb work of finding how they're connected to each other, right? So you start at the highest level and you say, okay, these are all these little dots that are going downwards apparently, right? So you mark them all, and the program will tell you when you missed something because everything has to be connected to something else. There are no kind of loose ends in the chip, right? So you start somehow, and you start connecting. You say, okay, here seems to be a wire that's running down here. Oops. And there's another wire that's coming down here. Oh, no.
This brings up a good point, Carson, what you just brought up. We're not seeing fake tracks anymore on these newer technologies since they've started planarizing going under the 500 nanometer range. ST used to do this. They'd hide tracks that had dead ends, went nowhere. Right. Useless logic. Carson would have realized this in D-Gate. Using the tool, it would have been like, hey, this is an open end.
Well, in fact, we did see that ends on one chip, so we kind of switched around the logic. There can be dead tracks, but everything still must be connected to something else. Right? So all that metal layer type obfuscation is of no relevance, really. So imagine somebody doing this for hours and hours, marking all these tracks on all the different layers. The tool then extracts the circuit diagram, right? It knows if there's a metal wire on top and there's a connection between two metal wires and there's a metal wire underneath. Those are all connected to each other, right? So it then exports a very rudimentary, Verilog representation of this chip, right? So you can imagine how somebody writes an Amazon Mechanical Turk plugin for this and has people do them at 10 traces a cent or something. So this is clearly not the bottleneck anymore. In fact, I don't know what the bottleneck right now is. We've been doing algorithm. I think the algorithm is here. Yeah.
I think the biggest bottleneck would be tracing out. The gentleman in the rear asked the question: tracing out where you want to focus on because it's so large today and it's just a sea of gates. There's glue logic everywhere, and follow the ROM really and look for flip flops.
Right.
Look for chain flip-flops.
In the big, what we call glue logic. So this type of a chip. Of course, if you just started taking images of everything and then had everything reverse engineered, you'd get a lot more information than you wanted to begin with, since really you're looking for the memory encryption function, and that'll be off this. How many gates are there? Maybe 100,000. Maybe 2,000 are spent on memory encryption, if even that. So if you could tell people to go about it a little smarter, see where the ROM bits the ROM lines come in, and then start with the gates really directly connected to that, and take the gates just after that, and the gates just after that, probably save a lot of time.
And remember, this is so you can then optically read out that ROM and not have to use any needles, because maybe you don't have needles, but you have access to microscopes.
Right.
And optical microscopes are good down to about 150, 180-ish. 180, I'd say, is about probably the best for most people.
Even with oil and all.
Yeah, wet immersion, some type.
So that's the tool.
So what type of technology are you seeing right now?
This one? That's an example.
This is the logic chip, right? This was like 800 nano. But for smart cards, the ones in the field, probably 500 down to maybe 200, 180.
Typically.
One's shipping now down 90. To 90. But nowhere close to what Intel or NVIDIA or anybody's doing. And so, but there's a tool-wise, there's a barrier at 180 nanometer. Everything smaller than 180 requires expensive equipment to image it, and that equipment doesn't really care how small it is then. So even a 32 nanometer, the FIP or the SAM would have no problem imaging. So really 9 nanometer is already a lot more secure than something a little bigger, just because it's not optically imageable anymore. Right.
The circuits are actually easier to understand in these smaller technologies as long as you've zoomed in than they were on the older technologies. Like that 600 nanometer process Carson just showed before. Those gates are crazy. Look at that same technology shrunk to 250, 200,
Oh, yeah.
220, sorry. It's much more clear and readable.
Yeah. So that's what the output of this tool looks like. A tiny snapshot of the output of this encryption function. And at this stage, then it's really just kind of reasoning about it. What did they mean with this? How do they process data? What could all these inputs be? Always acknowledging that this must be an encryption function. So there must be a key, maybe a key schedule. Not in this case, unfortunately. There must be some IV input. There must be some cryptographic structures. And we did in this chip find a 64-bit block cipher, one that's weaker than anything we've ever seen cryptographically, but that also solves a problem, or tries to solve a challenge that nobody else really has. Since this is a kind of in-wire encryption, the chip doesn't know it's there. It wants to access the memories in one clock cycle. This has to operate in half a clock cycle, right? So a 64-bit cipher operating in half a clock cycle. Nobody has a design to do this well. Even the old DES that's pretty hardware optimized takes, 16 clock cycles on this chip? So a lot longer than this. But long story short, there's this weak encryption function now that decrypts the ROM. So if you know this encryption function, if you know the ROM contents, the only thing that's missing is the key, of course, right? Now, where's the key stored? In ROM. It's right next to the code. So if you read out the code, you get the key with it. So this is really just building on the obscurity and secrecy of this function rather than the secrecy of the key. It's a scenario where you give the data and the decryption key to people as one packet and don't tell them what function you used.
Plus, we're dealing with smart card chips, but if you guys deal with any of these system-on-chip chips from these baseband processors, they don't even know what encryption is on that boot that baseband's boot ROM and such. It's all in the clear. Can you get to it, though, is another question. So we're dealing specifically on encrypted on memories we know are encrypted. But even still, like you said, the whole power-up sequence of this chip ran on clear code. The vendor never told you that, though. And the vendor would never tell you, probably would never even admit it.
Yeah, so the coverage of this encryption function is fairly limited too, we found. As Chris just said, the beginning of ROM has to be unencrypted, since at the very beginning, no keys loaded into this function yet, so it couldn't decrypt it. There's a little chicken egg problem, but it's not like the first thing the chip does is load a key and then decrypt everything else. There's a pretty substantial bootloader that's completely unencrypted, and that in some versions may even have bugs. So people could have read this out optically a long, long time ago without any of this knowledge. Then of the actually encrypted code, a lot, again, kind of disables this decryption function for some periods. Everything that's sent to peripherals, for instance, on-chip peripherals, is all in the clear, because the peripheral doesn't have its own decryption function. So of the actual relevant code, without knowing any of this, a lot could have been decrypted a long time ago.
Yeah, optical analysis.
Yeah, just optical. Take pictures, look at the little bits, figure out what that could mean in 8051. There's one little entropy problem you have to solve. They don't tell you which the order of the bits. There'll be some bit mingling. But of course, it's how many possibilities do you have to mingle 8 bits, right? And if you know, you have to look for some 8051 code. And you know that some of it is not encrypted, the entropy problem boils down pretty quickly.
Yeah, no, exactly. There's it's so easy in software to manipulate the bits to what possibilities it could have been, and see if you've got a chain of several opcodes that made sense afterwards to figure out their ordering, and then it's done. And the MAME world is doing this all the time, typing in old ROMs from the. They're very visible on the old days, and then the typing monkeys type them all in, and then they run them through their C code, these little Perl scripts or whatever, C scripts, and boom, out comes the ROM in the clear. And I scratch my head like, what the heck? How'd they figure out the ordering? It's weird, but pictures don't lie. That's the bottom line.
Yeah. So we're not going to release this function quite yet. We're still in a process of responsible disclosure, and this being hardware, it may take a little longer than the 2 weeks heads up period until the next Windows patch day. But we want to point out at least 3 interesting facts about this, since we don't want to keep it all hidden. First of all, this ROM in the middle differs by chip. Not by every chip, but every version of the chip, and clearly by every customer. So no 2 customers and no 2 versions of any operating system you put on here use the same decryption function. Neat idea, only the way they differ is by little ROM, and we already know how to read out ROM. So it's one more unknown you have to fill, but that you can read out in the same step as you read out the other ROM you want to decode anyway. So yeah, it's neat that they try to make it different and kind of force people to reverse engineer it over and over again. But doing it on this layer, probably not so effective. We've seen other chips where the customer of the chip, who I guess gets some part of the chip remade, usually the ROM mask, so some metal layer, but nothing else of the chip. Gets a little kind of Lego toolbox to play with, some area of the chip where there's gates that are not connected to each other, but the possibility of routing wires in between them. So that actually changes the algorithm in ways that you couldn't just fill in a blank after you did your analysis. Also crackable, of course, but there's some neat ideas how to diversify. So something tells me that somebody in this design group must have considered the reverse engineering threat 10 years ago when they built this.
That's a good point, though. 10 years ago when they built this,
yeah.
Nothing else was out there like this. They were pioneers in this industry for this type of principles, and it's still the strongest that I've seen today. I don't know, do you agree?
Right, well, the printer chip we looked at.
True.
Was that area
Right.
of kind of customer routable logic.
Right.
I think that was the only additional idea over this chip that has been.
But that was custom
stronger.
chip, though, or customized chip, versus this is a public chip. Everybody
Right.
orders the same type of chip off the shelf, as I like to say.
Yeah. So this by the way, was the most popular smart card chip for many years. So expected to be used in maybe even billions of units, definitely hundreds of millions, right? We hope that people will now start finding them everywhere and start analyzing these old protocols.
eBay, used SIM cards.
Used SIM cards, yeah. Yeah, like half of the SIM cards I've ever seen was exactly this chip.
Yeah.
2 other things to point out about the other areas of this function. So first, it uses 3 different keys. So it has key storage for 3 64-bit keys, one for its RAM, one for its ROM, one for its flash. So the ROM key will be the same for each version of a particular operating system, say. The flash key could differ per device shipped, and the RAM key actually differs every time you start up the device. It's randomly generated, and it is generated within its function. Took us a while to figure out what these 4 transistors do. They only have output, no input, so they actually generate randomness, and we measured it. They with Chris's needles, they do come out different. With quite a good randomness. So this is probably the tiniest random number generator that actually works I've ever seen. However, given that it has to store 3 64-bit keys for pathetic cryptographic protection, they spend way too much resources on key storage and way too little on everything else. Right? It's just, I guess, an insight into the level of cryptographic understanding. Right?
They did know there was a threat, though, because in the future they kept this was tightly coupled to the CPU core, and then they covered it completely with another layer of metal in the future. So they knew there was a threat, but they, like Carson's saying there, some of their focus was off focus, like implementation of the protocol.
And then one last thing to point out here. They did, as I said before, do a good bit of randomization of the gates, or obfuscation of the gates. Usually when you see simple gate like a MUX in these cases, you can immediately tell what it is. Well, after looking at the silicon zoo, you can, each of you. However, in this case, that's not true. You look at these gates, and they're way too complex for what they're doing. In fact, those two gates shown here on the bottom, they perform exactly the same function. And just look at them, how different they are. So they went way out of their way, actually spent extra silicon just so people could not reverse engineer it very easily. Now that tells us, though, after we did it now, that there's really no level of obfuscation people can't get around, right? There's only so much you can do without breaking the functionality of the gates, and I think they try to push that border. So that's telling you then, if you're interested in another chip, don't be afraid of obfuscation. In 90% of the cases, it will be much less obfuscation than this, and this has been done already now.
Right. And in the smaller versions of this chip, those gates weren't so obfuscated. They made a lot more sense, at least when I polished it down.
Yes, so they took out, in later versions of this chip, they took out some level of obfuscation. So it appears that at every scaling down of this function, the function in itself stayed consistent, but it of course had to scale down as the chip scaled down. Every time that they changed libraries, they did a little less obfuscation, and today it's really just standard cells,
very
except for the really big ones. But
right.
yeah, so somehow whoever thought obfuscation was a good idea, that thought was lost throughout the different generations.
Yep.
Any questions on this encryption function? No? All good? So then let's reason a little bit about how a threat like this could be prevented. And by the threat, I mean that 10 years after such a chip comes out, hundreds of millions of units with potentially weak protocols are at risk of being analyzed now. So the larger threat of this technological threat that somebody now breaks this exact same chip. And we believe that three things have to come together. First of all, it should be harder to reverse engineer chips, as much as that's possible anyway. Then the results of reverse engineering should be much less relevant. So optimally, somebody could reverse engineer everything and still not learn anything, right? And lastly, and I think this is a crucial point that's not made often enough, there shouldn't be a reason for people to try this in the first place. There shouldn't be anything hidden in these chips that's valuable enough so you'd spend all that time and energy. So if it's just a secret key of, say, a bank card, how much can you possibly steal by copying a single bank card, right? Whereas this now, as we keep saying, targets numerous applications in numerous industries, all of which have hidden secrets, not in single instantiations of cards, but across all of the cards. Software errors in Java frameworks and so forth, right? That's a real incentive for people, and that needs to be prevented, right? Sure, go ahead.
I gotta take exception with that last one, because you're basically saying that, throw out the technology. The whole motivation for people adopting this technology for stupid things like medical records and all the other stuff that they want to use it for is because they're trying to come up with a secure storage medium to transmit this data. You're basically saying, don't do it. Right? I mean, you're saying
No. That's
don't make it worthwhile to hit it, to attack it.
Okay,
So let me
do that then, because again, the mindset of the executives that are saying go out and spend money on smart cards to implement some sort of a secure solution is that this is going to provide them that solution, and they want to put that valuable information in that medium. You're arguing against that. Tell me how to do that.
So the gentleman in front, for those who didn't hear it, is saying we are criticizing the whole idea of using smart cards and pushing people not to. And that's not even close to what we're arguing. So what we're saying is, don't take this little fortress that's built to protect your RSA key and take that fortress and put your own proprietary algorithm in it and use it instead of RSA, for instance. Don't try to create a level of non-auditable proprietary security that gives you a competitive edge just because the smart card provides the protection to get away with it.
Or it's believed to provide it, which we've proven every smart card to date that's ever been manufactured by any manufacturer has been broken if there was a reason to break it for market share, for market value. Pay TV is a perfect example of it. NXP, Renesas, Atmel, ST, who am I missing? Infineon. They're all broken. At least on one of their chips have been broken. Nothing's secure unless you customize, and And I think the best person, the best company out there to explain about, to demonstrate is NDS for DirecTV, for Sky in the UK. They went to ASICs 15 years ago. They're ahead of everybody else.
But that's a little bit confusing, the discussion, since in pay TV, right. What I just kind of claim as the known holy grail of security, use a known security tested encryption function and try to hide your secret key. That of all the industries does not work in pay TV, since they're extracting even the secret key from one card gets you the access to everything. So they have a completely different threat model from everybody else. But excluding pay TV, all the industries you were just naming could use well-established security primitives and try to just hide the secret key. That's what smart cards were invented for. They're not invented to cover your Java JVM vulnerabilities. Right? Everybody got that? Any more questions? All right, so the three things we would want from smart cards for this to not be a threat in the future. So if we, again, in 10 years look back and ask how many people did put algorithms in these chips that then in 10 years are heavily exploitable, for this to not happen, first of all, reverse engineering should become more difficult, which is already happening, not necessarily for security reasons, but kind of as a side effect of technology scaling. Chips both scale down in size and scale up in complexity, so more and more functions are put on there. They started with a DES encryption, and now they have DES and AES, and they add RSA and ECC. There may be different chips merged into one to add some multimedia functionality, or whatever the trend is. It's getting more and more complex to take pictures of them because of their small size, and to figure out the relevant part you want to reverse engineer because of their complexity. So that's a good trend. And if you have the choice of, an older 200 nanometer chip and a newer 90 nanometer chip, that makes all the difference in the world, at least for somebody who sits at home with an optical microscope. Right?
I've seen a lot of people in 180 nanometer well process with the metal at like 150, 140-ish. They're making things as tight as they can to shrink, keeping it at an aluminum process, I think for costs. I don't know.
Yeah, only for cost, not for security, but there's a very positive security side effect.
Yeah.
So in addition to that, I think the threat of optical ROM readout also needs to be solved structurally. First of all, the truth that once you read out the ROM, and the function, you got the key kind of for free while reading out the ROM, that doesn't have to stay a truth. There's nobody saying you have to store the ROM key in the ROM. It may complicate the production process just a tiny bit, and we'll change a little bit of wiring on the chip to store it in flash instead. And this being a 64-bit key or a little bigger if you want to be future-proof, let's say you spend 128-bit of flash on storing the ROM key. There's already many dozen kilobytes of flash, so it certainly wouldn't hurt cost-wise.
There's already 64 bits at least of trace data from the factory that could be half the key anyway, and then have another 64 bits of space.
True. Yeah, that's a good idea.
Yeah, of course.
Write a patent on that. They can throw mucks. They already do throw mucks in this implementation here of when to be clear and when to be encrypted. And so they can, because what they'll say to you is, well, we can't store it in flash because we don't know what flash is out of the factory. Well, you don't need to now. You can load it through this clear code that you've got anyway, and load it from flash. Because now you can't see flash. You can't store charges. And so it's nothing to see. Now you need needles. So once you do that, once you did store the key unreachable for somebody who doesn't have a FIP and microprobing needles. You still have to ensure, though, that people can't infer the key from the data they're seeing in the ROM. And with the level or lack of cryptographic hardness of the function we have seen here, you can easily infer the key from guessing, what would be in the ROM, say the last parts of ROM being empty. You can infer what 64-bit was used to encrypt it without looking at the key itself. So this calls for more cryptographic strengths, but in a world where no cryptography has been built yet, one clock cycle block ciphers, right? So this is a research challenge really for everybody to come up with more lightweight block ciphers that, giving a little bit of known plain text can cover still
area.
cover up the key. It doesn't have to be AES grade. There'll only ever be a certain amount of plain text. There'll only ever be a certain kind of level of incentive. Nobody wants to break this as badly as they want to break some AES keys.
But there is one, just to give a positive to this function, we've been slamming it all hour. Your data's from EEPROM, statogram are not code running, so that they would be encrypted a lot better than codes running from EEPROM or ROM. So it has its purpose.
Basically, what you're saying, people should start hiding their Java vulnerabilities in Flash. Flash, of course, is a lot more expensive, so there'll probably always be ROM, at least in high volume chips. So once you did the second step too, hardened it cryptographically, that is took away the incentive for people to, the relevance of the results you get from a reverse engineering. Now you get a cryptographic function and you see the data, but you don't see the key anymore. In fact, at that point, it would probably be good to publish the cryptographic function, right? Have people analyze it, have a whole research world built around it. So in addition of all of this, we'd still want the incentives for breaking smart card chips to go down. Probably the most obvious step would be, if you're a smart card manufacturer, don't sell a pay-TV card anymore, right? Exclude those couple companies, and 90% of the hackers won't look at you anymore. But even in less high value industries, that it's relevant to keep the extractable amount of money low. And here's a little war story from a project we did years ago. So a payment card used in France uses what back then, when this was issued, may have been the best smart card, or one of the few. It was the first smart card with a mesh ever. So it was definitely ahead of its time. But it's old, and they don't want to replace all the smart cards, of course. So even though this is a highly outdated smart card, for the street price for breaking it probably still runs 30,000 or so. Now, for a payment card, you'd not spend 30,000 to copy one of these to get free subway rides and train travel in France, right? Maybe. You have to go a lot of trains, though. The same chip, however, is also used in the reading terminals, and these are all over France, in remote locations, easily accessible. They're often vandalized, so they lose a lot of these reader chips. And now the same chip has to protect the master key of this entire country. Given that key, you could create as many payment cards as you want. Now all of a sudden, at 30,000 price token for breaking it isn't all that high anymore, right? The chip didn't change though. Same chip, same exact protection level, however insecure all of a sudden, right? And that should, if there's any system designers here, of course, give you some food for thought how to diversify the value across the different cards to the point where no single chip carries attack incentives of whatever you expect the protection level of your chip. Not to be today, but in 20 years when you find your application to be very successful and you have millions of cards in the field, right? So the risk management process, extrapolate from today's attack cost 20 years into the future, however long you'd expect your very successful system to live, and make sure that no card ever chips with attack incentives even close to that cost, right? So nobody would want to attack that. And I think with that, we're pretty much done with what we wanted to tell you today. Hope we encouraged some more curiosity into smart cards, especially among software people. I hope this does take down some mental thresholds. We are software. We don't look at hardware. If you don't want to take pictures yourself and extract these codes yourself, but you do have an interesting research project you want to work on, get in touch with us. We're always looking for interesting projects. I'm happy to help you extract your vulnerable Java implementation or whatever you have. Right?
We've already done that.
Yeah, we've done it, but there may be more
out.
than just those three manufacturers. Yeah.
Yeah.
Yeah. And what chip is in there, you know?
I have no idea.
So is this an Android phone?
Yeah.
Probably there's no TPM in there. There will be soon.
It's
the
gonna be an
secure
ARM.
element. Yeah.
Yeah, I know. I figured you'd get a head start.
Oh, there's a SIM card in there, though.
Yeah.
That may do. Yeah.
The baseband's an ARM. That's given. There's nothing else in use that I've ever seen. It's always ARM based.
Right.
The different talks, but I mean, in terms of handsets and, you know, physical security in the handsets, non-existent. Feel free to say if you know anything.
Right. So, but with that, thank you very much for your attention.
Thank you, everybody.